much about the schedule. All right, here we go. On the current slide. All right, 5 different reaction types. We're going to briefly repeat the combination reactions as we've taken it today. All right, so reaction types. Combination reactions have to do with taking 2 small things and reacting them together to make one larger thing. So you take 2 smaller reactants, which combine together. There's a nice YouTube video that you might want to take a look at. The example we might write for a combination reaction could be the Haber process. Haber process, we took nitrogen gas plus hydrogen gas and make ammonia gas. So there's the basic skeletal equation. If we want to balance this equation, put the coefficients when we put in the front of each of these 2 things. Balance this. I got 2 ends here and only 1 here. So how can I fix that? Put 2 in front of here, right? I can't do this, right? That's wrong. I can't change the nomenclature. What I can do is simply make more than 1 molecule of those being produced. So now I've got 2 ends there and 2 ends here. I have 2 H's and 3 H's. So what do I need to do? Well, actually, I don't have 3 H's there. How many H's do I have? 6. 2 molecules times 3 H's per molecule. 2 times 3 is 6. So how can I make 6 hydrogens on the reactant side? Alright, so now this equation is balanced. Follows the law of conservation of matter, which says matter cannot be created or destroyed. So what it says is I've got 1 piece of nitrogen, right? Single diatomic molecule. This is in the microscopic perspective. This is symbolic. Micro might look something like this. I've got 1 molecule of N2, and I have 3 molecules of H2. And they combine to make 2 of these NH3s. So once again, matter cannot be created or destroyed. It only is switching partners. So if the N is the open circles and the H is the closed circles, and we count how many of them we have on each side, we've got 2 ends here, 2 ends here. 2, 4, 6 H's, 3, 6 H's. So matter hasn't been created or destroyed. And that corresponds to this idea of a combination reaction. All right. Good examples of combination reactions are there. The next one is sort of opposite of a combination reaction. It's a decomposition reaction. Oh, by the way, combination reactions are also known as synthesis reactions. S-Y-N-T-H-E-S-I-S. Synthesis. Biologists like to use the word synthesis to depict combination reactions rather than combination. Decomposition are basically when one thing breaks down into smaller components, kind of the reverse of a combination reaction. Good decomposition reaction that I used to like to do demonstrations of, that is something you've probably seen in your own common experience. Is decomp now. We've ever used hydrogen peroxide. What's the formula for hydrogen peroxide? H2O2. What symbol would I put next to it to depict its state of matter? Little L. We're going to assume that it's a relatively pure solution here. The decomposition of hydrogen peroxide, you can see happen. If you take hydrogen peroxide and you pour it on an open wound, my mom used to do this when we were little kids and we would skateboard a lot. You fall down and scrape up your knees, right? You come in, your knees are all bloody, they got the asphalt and the dirt and all the junk and the bloody wounds. And she takes hydrogen peroxide because that's the most gentle and humane way to get the dirt out. Because what happens when you pour hydrogen peroxide on a wound? It bubbles. It's not an antiseptic. It's not going to kill the bacteria and the germs. What hydrogen peroxide does when it bubbles out is bubbling out the dirt and the asphalt and the grime out of the wound because it is catalyzed. The decomposition of hydrogen peroxide is catalyzed by any organic matter. So if you take anything, a piece of meat, a carrot, an apple, anything, and you take some hydrogen peroxide from the drugstore, you know, the stuff they sell in the brown bottles, and you put a hunk of those things into some hydrogen peroxide, you'll immediately see it begin to bubble. So as it's decomposing, what do you suppose it's making? What is it decomposing into? That would be a good guess. One of those is true. The guess was hydrogen and oxygen gas. Well, one of those is true. What gas do you suppose is being produced? Oxygen gas. That's one of the things that's being produced. And how would I symbolize the state of matter for oxygen gas? With a little g next to it. All right, in addition to oxygen gas, what must be left over after some of those oxygen gas bubbles bubble out of the solution of H2O2? Good old water. Good old liquid there. All right, so hydrogen peroxide decomposes into oxygen gas and water. Organic matter can catalyze this decomposition, but also other things can catalyze the decomposition, like these are what we call photocatalyzed. Photocatalysis. What is photo? What's the preview of the prefix photo? Catalyst. Light. So why does hydrogen peroxide and those brown bottles in the drugstore? Because they want to keep the light out. Because if they didn't keep the light out, what would you be buying a bottle of? Well, the bottles would all bubble out, right? They'd be above the water, and what you'd be buying is a nice brown bottle of water. You don't want a nice brown bottle of water, you want a nice brown bottle of hydrogen peroxide so that you can decompose it when you want it to, right? So it's photocatalyzed. When you light it to the hydrogen peroxide, it will catalyze it and make it decompose. How can I balance this equation? Right, because I've got oxygen in two of the products. I've got an oxygen in the water, I've got an oxygen gas here. So I have to account for both of them as being on the reactants, supposed to be on the product side. So how can I balance this H2O2 plus O2 into H2O? Any ideas? Two water molecules? Let's try that. Two water molecules would be 4 hydrogens and 2 4 oxygens. Over here, I have 2 hydrogens and 2 oxygens. What should I do? 2 here? Okay, so then that gives me 4 oxygens and 4 hydrogens, but how do I fix the oxygen? So it's all good now, right? So we're all balanced. This now follows the law of conservation of matter. If you look at our stockroom, at the drugstore, they give you the 3% bottles. It's in the brown bottles. If you look at our stockroom, in the chemistry stockroom, we have 30% H2O2, which is basically 10 times as concentrated as the 3% that you buy at the drugstore. Our hydrogen peroxide that we have in the stockroom, the bottle looks like this. It has the lid on it. And these little parts right here are sort of accordion folds. And when this doctor attendant puts the bottle on the shelf, she swooshes the folds down, puts the lid on, and then sets it on the shelf. And then over time, the folds sort of grow, right? And the bottle grows, and the lab tech has to come to the stockroom, unscrew the lid of the bottle, swoosh it down, screw the lid back on, and do this. Why does she have to do that periodically? What's happening in the bottle of hydrogen peroxide? It's 30%. It's decomposing right there. The oxygen is also brown, but it's brown plastic bottle. So as it decomposes and the oxygen gas is released, it's contained in the bottle. She's got to unscrew the lid, swoosh it down, so it goes down, and then she will have to decompose a little bit more. So we have the 30% provided of the hydrogen peroxide. If we look at other reactions, whoopsie. The first one is calcium carbonate. Here, you look at the calcium carbonate. Solid. That's just shells from sea animals. You take shells from sea animals, they can break down into calcium oxide and carbon dioxide gas. Potassium chlorate. This is stuff, if you've ever seen a demonstration where they take orange powdery stuff and you put it in a volcano. Like, remember in junior high science when you made a volcano? And sometimes you would put vinegar and baking soda, right? That made kind of an interesting sort of a bubbly thing, but that really didn't look like lava. This stuff, this potassium perchlorate or chlorate, KClO3, is an orange powder. You put it in the volcano and you light it on fire, and it makes a fire that looks just like a volcano. The ashes come out, so it's really kind of cool. And the last one on this list, the NaN3,
That's sodium azide. The common name for that is sodium azide. Does anybody know what sodium azide is used for commonly? It's in your car. That's what is the rapid deployment of airbags, right? Well, rapid deployment meaning when there is activation energy, they have a little trigger, a little tiny explosion inside the sodium azide that triggers the reaction. It produces sodium solid and nitrogen gas. And why do you suppose they wanted to produce nitrogen gas instead of something like, for example, maybe hydrogen or oxygen gas? Okay, hydrogen would be a bad idea in a car accident in your airbag. Why? It's explosive, right? You don't want that, a big giant bag of hydrogen gas right in front of you. Okay, what's wrong with oxygen gas? It's not explosive, but it's right. It supports combustion. It's very flammable. So we don't want hydrogen or oxygen. So nitrogen is what we call an inert gas. It's not going to react, so it's very easy in an airbag. If you've ever been in an automobile accident where the airbags deploy, all of a sudden the airbags come out and all this white powder goes out everywhere. Everybody thinks it's smoke. It's not. It's actually talcum powder. Because when the airbags deploy, they deploy very quickly, and that sodium azide has to produce that gas super fast. This reaction happens really, really quickly, so that nitrogen gas fills up the bag. But then it also has to deflate at the same rapid rate so that you can get out of the car. Because once the airbag deploys, it kind of smooshes you back in your chair, and it makes, especially the side curtain ones, it makes it really difficult to get out of the car. So they have to deploy and decrease so that you can get out of the car, and they have tiny little holes in each of the bags and a whole bunch of talcum powder in the bag. So after it inflates with the hydrogen gas, then it deflates very rapidly, and the little talcum powder that comes out of the holes makes a big cloud in your car, and everybody thinks it's smoke, but it's white. So it's not truly smoke. If it were smoke, it would be black. So if you are in a car accident and the airbags deploy, don't freak out with all the white powder. It's not smoke. It's actually simply talcum powder, which helps the airbags deflate at a rapid rate. Yes?
Second example with the potassium chlorate. How do you go from 6 oxygen from the
That's not balanced, is it? Absolutely. So what should we do to fix that? That must be a typo on my part. Oopsie. What would we do to fix that second equation? You're absolutely right. It's not balanced. How would I fix that second equation? Put a 3 in front of the O2. And I think that would fix things, wouldn't it? Wouldn't that fix everything? Yep, it sure would. Thank you for noticing that. I got to fix that. All right. All right. So if we go into the next one, before we discuss single and double replacement reactions, we've got to discuss the idea of what happens when we put salts in water. Remember, salts are ionic compounds. Anything that's a binary ionic compound or a ternary ionic compound, chemists classify under this major blanket classification system called salt. So there's literally hundreds of different kinds of salts. And a salt is a metal, non-metal combination. So in this particular animation, I am going to show, and we're going to talk about it as we go through the animation, because this is super crucial to your understanding of what's going on in an aqueous solution, right? We put that little AQ. You take ionic salt and you put it in water. We're going to make an aqueous solution. Oops. Come on, you two. There it is. Actually, we'll do full screen on theater mode. All right, here we go.
Sodium chloride crystals are held together by attractive forces between the...
Oh, it's buffering. All right, we got the sodium ions, which are positively charged, the chloride ions, which are negatively charged. The difference between the electrostatic attraction is what keeps the whole thing together, right? Repeating crystal structure of NaCl, NaCl, NaCl in all 3 directions. Okay, so that's what they're talking about here. Now, we take this salt crystal, and I like this because it's the microscopic perspective, and they'll show the salt shaker shaking out the salt from the macroscopic perspective. So that's what you would see when you're shaking the salt into the water. The microscopic perspective is what happens to this crystal once the water molecules come up close to the crystal. I don't know why it takes so long to buffer here on my laptop. Is that because I have other things open? Is that why it takes a long time? Those of you that know technology better than me? Sometimes if you pause it and start it again, it helps.
positively charged sodium
until it gets to the point that it had to buffer. Oh, wait a minute. No, don't go away. Did I just mess it up? I started it over again, didn't I? Did I? See, this is what happens when old people try and use technology, right? I screw it up. All right. Well, you know what? I could describe to you what happens when you All right, we don't want a nature video. Oh, well, let's see. A water molecule. All right, I like this so far. Oh, well, this is good. So there's the sodium chloride, and the water molecules climbing up next to it. And all of a sudden, they start to pull the individual ions off. And that's because one side of the water molecule is positive. The top side is positive. The bottom part is negative. And so what happens is the ion, in this case the sodium chloride, also has negative and positive charges. So the polarity of the water molecule allows it to turn and move, and the water molecules start to gang up on one of the individual ions, right? So the sides of the water molecule turn towards it, and they attack the individual ions on the crystal, on the outside of the crystal, and maybe one water molecule is not going to have the force to pull the ions apart, but multiple water molecules grab onto it, because here's what happens. You got a sodium and chloride bonded together, right? There's an attraction, a force that holds them together. But if you have a force that's greater than the force between the sodium and chlorine, meaning the force of multiple water molecules grabbing onto that one chloride ion, multiple water molecules' force can overcome the force that the sodium and the chlorine feel for each other, and it pulls them off the solution. All right, Canadians, thank you. That was nice. All right, so let's see. Let me draw a picture of what I think that kind of looks like, in my mind at least, right? When I was in school as an undergrad, we didn't have computers and animations and visualizations. We kind of use our imagination. So if we're talking about sodium chloride, we've got NaCl, 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 you're repeating crystal structure. Okay. So here's our crystal. The water molecule comes up. We haven't talked about molecular geometry yet, but what you do at this point is that the water molecule is positive on the side that the protons, the hydrogens are, and negative on the side here where the non-bonded pairs of electrons are, if you remember the molecular geometry. So it's a very polar molecule. Sodium and chlorine is also polar. Sodiums are positively charged, chlorines are negatively charged. That's why they stay together, because these two are attracted for each other. Right? There's a force of attraction between them. So it's hard to pull it apart, and that force is called the bond energy. And every compound has a different bond energy associated with it, and it has to do not only with the types of atoms involved, but how many of them are there. Right? So there's bond energy that it takes to break that up. So water molecule has to overcome that bond energy. So water molecule comes up to chlorine on the very end of this molecule and says, the positive side of the water molecule then will orient itself towards the chlorine. Lots of water molecules will gang up on the chlorine, right? See how I oriented them with the positive side towards the negative chlorine? They break that bond, they pull the chlorine off, and then they surround him. The first process, the first step here is called dissociation. And that involves the bond energy, the taking of the pieces away from each other. The second step is called hydration. Hydration happens when little water molecules kind of make like a little buffer around the chloride ion. So we have this negatively charged piece. Here's my solution that I've dropped a sodium chloride crystal into. And now, after I drop the sodium chloride crystal into there, the chloride ion is moving around. It has this little buffer of water molecules, and you can see that the positive side of the water molecules have all oriented themselves to the chlorine. Well, the same happens with the sodium, except the opposite is true. The negative side of the water molecule then will orient itself towards the sodium. They all gang up on a sodium ion on the outside, and they pull it off of the crystal. And the sodium ion now is by itself with a little plus charge, and it is also hydrated.
right? So the first process is called dissociation, the second is hydration. Now with the hydration of sodium, if you look at the water molecules, they have oriented themselves exactly the opposite as the orientation around the chloride. Here, the positive end is away from the sodium, and the negative end is towards the sodium. So these are ions in solution. We call those electrolytes. Right? Ions in solution, we call those electrolytes. Electrolytes conduct electricity. And that's super important. We need electrolytes, right? Gatorade. You drink Gatorade and you do a lot of exercise and you sweat out a lot of electrolytes, and then you feel kind of lethargic and tired. And that's because your cells cannot communicate as well to each other because they need the electrolytes for the electrical current to pass through. Your brain doesn't work as well because the synapses in our brain need electrolytes for the electrical current to conduct through. And what makes the solution conduct electricity is the presence of ions. If you have a solution of purely distilled water, only H2O, and H2O water molecule is neutrally charged, meaning it doesn't have an overall charge associated with it, it will not conduct electricity. Meaning there are electrolytes in it. Anytime you put a soluble salt, another vocabulary term, soluble salt into water, that soluble salt will break up into its component ions, and now all of a sudden that solution will conduct electricity. This is a big difference. Non-electrolyte has no ions in it, it will not conduct electricity. Electrolyte has ions in it, and it will conduct electricity. And it turns out, when we have this aqueous solution, now we would have NaCl, AQ. And that's the symbolic representation of a sodium chloride aqueous solution. And in our mind as chemists, we say, all right, I know to make that aqueous solution, I have to take NaCl and I have to put it in water. But in my mind, I also think of the microscopic perspective, where the sodium ions and the chlorine ions have broken up, and now they are available to go through chemical reactions. And that's super important because as a compound, sodium chloride is not very reactive. You have the salt right there, it's fairly inert, it's not going to react. However, once you put it in water, and you break those sodium ions and chlorine ions up from each other, now you have much more potential for reacting. So aqueous solutions are super important to your understanding of chemistry because of what goes on. Not only are the aqueous solutions important, but the ratio of the component ions that you're dissolving is also important. For example, if I take, now that was an example of a binary ionic salt that we put in water. If we take something like a ternary ionic salt, say for example lead nitrate, ternary, I take lead nitrate and put it in water. Lead nitrate is always soluble. And that term we'll learn a little bit later. What that means is when I put it in water as a chemist, soluble means to me that it breaks up into its component ions. Alright, so what kind of ions would be produced when I put lead nitrate into water? What would this break up into? Here's where you have to use your knowledge of nomenclature. And if you don't know nomenclature, this part of the course is going to start to get difficult. So if you wanted to break that out, what would the component parts of it be? There'd be for sure some lead ions, wouldn't there? What would the charge of the lead ions be? A +2 charge, right? What else would be floating around in there? Nitrates. And nitrates are a polyatomic ion. So we symbolize them like that, but in your mind's eye you say, oh, I know nitrate really means this, right? That it's one nitrogen and 3 oxygen that hang together as a group and carry with them a negative charge. So we symbolize it like that in my solution, but in this case, it's a 2-to-1 ratio. That doesn't mean I'm going to take just one piece of this and put it in water. That's impossible, right? You can't take a single piece of an ionic compound. I got to put a whole hunk of it in. But what I'm showing with this microscopic perspective, the ratio of the ions that I produce is a 1-to-2 ratio, and that turns out to be super crucial later on in this course, and especially crucial when you get to Chem 152. Right? So say, for example, let's try one more. I tried something like calcium phosphate. Calcium is +2, phosphate is -3. If this is soluble, and I put it in water, what kind of ions and what would be the ratio of the ions that would be involved here? What kind of ions would I have in my solution here? I have some calcium. I have 3 of them. What would the charge on the calcium ions in that solution be? They all be +2, right? That's super important to recognize. They'd all be +2. What other kind of ions would I have in there? I'd have some phosphate ions. I'd have some PO4 with a 3- charge too. Now, once again, it's impossible to just put a single piece of that in there. But it's important to recognize that the ratios of the component ions would be a 3-to-1 calcium to calcium phosphate and a 2-to-1 phosphate to calcium phosphate, right? Okay, so that's
Ions in solution. And there's a couple other PowerPoints there that you can look at for salts dissolving in water. Which brings us to the next kind of reaction I want to talk about, which is called single replacement, sometimes also called single displacement. Also, by chemists, we sometimes use chemistry slang here, we call them redox reactions. Redox reactions are where a metal comes into contact with an aqueous solution. So let's look at what that would look like. All right.
Single replacement. General form of a single replacement reaction, just like general form for silica line, is going to be, so single replacement is going to be some metal solid, okay, plus some aqueous solution. So in your own mind's eye, you go, all right, aqueous solution, that means I was going to look at this from a macroscopic perspective. What would this look like in lab? And you're actually going to do this slide in the next couple of weeks. You're going to have an aqueous solution. I'm going to put this BC in my aqueous solution. So in my own mind's eye as a chemist, what does that mean actually floating around in the aqueous solution? B ions, which have a positive charge. And how do I know they have a positive charge? Because the metal always appears first, and the C ions will be floating around, right? So in plots, I plug my A. A is a metal, right? Solid. And it sinks to the bottom of the container. So here's my A solid. What's going to happen is, if, we use the calculus if. What's different about regular if versus calculus if? Besides an extra F. Come on, calculus people. If and only if. Alright, so if and only if A is more active than B, reaction will occur. Alright, so how do I tell if and only if A is more active than B? Does anybody know the reference we would use to determine if A metal that I plugged into my aqueous solution was more active than the metal ion B? How would I determine that? It's called a reaction charge called the activity series. It's the activity series for metals. What that is on the periodic table that I gave you, and it's on the back of the periodic table that I gave you. Here's the activity series for metals. Alright? So this is your reference for single replacement or redox reactions. So these are the ones that are the most active. These are the ones that are the least active. No, I will give you that exact reference as well as the solubility rules on your second unit exam. For the first unit exam, you will not have to predict if the reaction will occur. You'll just have to look at a single replacement reaction and say, yes, that's a single replacement reaction. Okay? For the second unit exam, you will have to predict if they occur, and you'll learn how to use this activity series much more efficiently in lab. Alright? So we're working on that in lab. But that's basically what you're going to use. So the activity series for metals is helpful reference for this. So if A was more active than B, what would happen in my pretend equation here is B then would become a solid, and AC would now be my new aqueous solution. So that's the general form for the equation. What I'm going to do here is I'm going to show you an animation. Whoopsie. That actually shows this happening, which is from Iowa State.
They had some grad students that did some really cool things. All right. This is the Iowa State website, and it shows how you can do single replacement reactions virtually. It's kind of cool. So you go in. This is the link that's in your PowerPoint, so it's already there. You go in, and what it does is it gives you a whole bunch of ionic solutions. So here I've got some magnesium nitrate, some zinc nitrate, some copper nitrate, silver nitrate, right? All right, so I'm going to go to Activity 1. In Activity 1, I'm going to pick one of those metals to put into the 4 solutions. So I know that, let's see, what's pretty high on the activity series? I'm going to pick zinc. Zinc is a fairly active metal. So now all of a sudden, the animation shows I've got 4 hunks of zinc that are ready to be lowered down into my aqueous solution. Well, if I think about the aqueous solutions, what kind of ions am I going to have in this first aqueous solution? Magnesium and nitrate. What about the second one? What am I going to have? Zinc and nitrate, so that's probably not going to do much with zinc metal and zinc ions, right, because it's the same thing. What kind of ions am I going to have in this one? Copper and nitrate, and the last one I'm going to have silver and nitrate. Okay, so what I'm going to do now is I'm going to place the metals in solution. As you can see, they're all nice and gray right now. Look at also the color of the solution. The first 2 solutions are clear, the third one is blue, the fourth one is clear. All right, I'm going to click that, lower down the solution. Look at how the colors of the solutions change. All right, did the first 2 solutions change in color, or did the metals change in their appearance at all? No. So macroscopically, we would say there's probably not a chemical reaction that occurred in those 2 vessels, right? The first 2 vessels, would you agree? This one and this one, it doesn't look like anything occurred because the solution didn't change color. There's nothing that appears to be deposited on the metals to me. So I would say nothing occurred. And we could verify that, and we'd say, okay, well, I know that's zinc. Magnesium must be less. Let me think. If and only this part of it. Let's go back to, whoops. All right. That first slot, we had magnesium. What was this? This was magnesium and nitrate. And we put zinc in it, didn't we? And there was no reaction. So there would have been a reaction if zinc had been more active than magnesium. But since there wasn't a reaction, what can we say about the activity of zinc and magnesium? Who must be more active? Magnesium must be more active than zinc, so therefore reaction didn't occur. Oops. I want the little p. There's the little p. All right. Oh, actually, I wanted the animation, didn't I? Where's the animation? Where is it? There. Thank you. I'm learning. All right. So now we can say that copper, there was the copper container. What do you notice about the color of the solution in the copper container? It got less blue. Did you notice that? All right. Copper ions in solution give a solution a blue appearance. So if it became less blue, what must have been taken out of the copper ion solution? The copper ions. There's a coppery colored coating on the zinc. What do you suppose that coppery colored coating on the zinc is? Copper, all right. So I would say there was a replacement reaction that went on there, right? We'll talk about that in just a minute. And the last container, the color of the solution didn't change, but what did change about the solution? It got a little cloudy, didn't it? That's generally an indicator of a chemical reaction. It also looks like there was a precipitate or a coating on that zinc metal. Does it look like there was some kind of coating that happened on the zinc metal? So I would say there was probably a reaction there. Now what I also like about this particular animation is now you can look at the molecular scale. So let's take our, let's see, it was zinc. And we're going to put it into the copper solution, because that's when we knew reacted, right? That's when we got the precipitate. So we're going to start it. So the water molecules and nitrate ions are not shown. Here's what happens. All right, I love this part. Okay, the zinc metal's in there, the copper ions are floating up. Boom! Dang! How cool is that? Let's try that again. That was so exciting. All right, now, you know what, before we do this, let me toggle, and we'll talk about what's actually in the solution there. That animation, we have
solution of copper nitrate, right? Isn't that the stuff I put in there?
What must have been the ions floating around in my solution,
My aqueous solution of copper nitrate. There's the symbolic. Microscopically, what should we be thinking about when we're thinking about the solution of copper nitrate? Copper ions with what kind of charge? +2, and what else? Nitrate polyatomic ions, each of which have NO3 minus charge, right? Alright, so then in pops my zinc. Here's my zinc solid, right? Is that my zinc solid? So now I'm going to run a reaction for this. I say my zinc solid plus the copper nitrate aqueous solution is going to make something else. So that's my symbolic representation. There's my microscopic idea of what it is that's going on.
let's look at the macroscopic now that they give us on the animation. We will do that in lab. We're not going to do that in here, but that's a good point. Yes, we do analytic equations. Okay, I want the animation. Help me figure out which one is the animation. Third one? There it is. All right. So the water molecules and the NO3 ions are left out, right? So they're just showing you the copper ions and the zinc metal as they approach each other. And this is the crucial part of redox. All right, copper ions are floating up. They have a +2 charge. That means they are missing 2 electrons. What happens when those copper ions that are missing 2 electrons hit the zinc? Zinc does what? Gives them each 2 electrons, right? The copper ions, when they were floating towards the zinc, we look at that again. The copper ions floating towards the zinc, look at the size of them. They're small. Once they grab electrons, what happens to their size? They get bigger. Let's look at that again in terms of the size of the zinc ions. The zinc atoms are big. Watch what happens when they give up an electron. They become smaller. Doesn't that make sense?
If you have 2 valence electrons and you give them up, aren't your valence electron shells going to shrink? If you have
a shell and you have extra electrons put in, doesn't it make sense that it's going to get bigger? What was that copper-colored coating we saw on the metal? Copper ion, or copper atoms. They used to be copper ions in solution. Once they grab those electrons, they're copper atoms. This process is called electroplating. We do a lot of electroplating in normal everyday life. Here's the humanistic perspective. You drove to school today in a giant automobile that had 2 giant electroplated hunks of metal on the front and the back of your car. Those 2 giant hunks of electroplated metal on the front and back of your car. They're silvery colored. Exhibit if you got chrome bumpers, right? Okay, so we got chrome bumpers. Well, chromium is the element that the chrome bumpers are electroplated with. What's underneath chromium? Iron. Iron. So if you have a big honking giant bumper made of iron, which doesn't cost a lot to make, because iron is cheap, right? They put it down in a giant vat of chromium ions. That happens. The chromium ions cling to the iron. And now you have a nice shiny bumper that's not going to rust, because chromium doesn't rust or oxidize as readily as iron does. And you put a nice shiny coating of chromium ions over your iron bumper, and all of you look good, it's not going to rust. If you made the entire bumper out of chromium, that would cost you a whole bunch of money, right? Unless you're driving a Lexus or a Lamborghini or something like that, right? You don't want to spend that kind of money on your bumper. So this is the process of redox. Redox is chemistry slang for oxidation reduction, and redox has to do with electrons being transferred during the process of a chemical reaction. The type of visual evidence you will see in redox reactions are either a precipitate being formed like this, where it's being coated on the metal, or some redox reactions you'll see a gas being formed. What kind of evidence visually indicates that a gas is being formed? Bubbles. All right, so single replacement reactions, your evidence is either a precipitate being formed or bubbles being formed, and we're going to talk about the definitions and why those are true more in the lab. But that's just the big picture idea of what a redox reaction is. Okay, so that's single replacement redox reactions. There's lots of demonstrations of what macroscopically a single replacement reaction looks like. Once again, I'm not going to go through these in class. I expect you to do that. to look at these to see what it is. Now we're going to talk about double replacement reactions. Double replacement reactions are reactions in which we have two aqueous solutions. Right? Single replacement reaction, we have a single aqueous solution, and we put a solid metal into it. Right? So you have salt with ions floating around, you throw in a hunk of metal that's in solid form. Double replacement reactions, we have aqueous solutions of ionic substances that we add together, and the evidence that you're going to see is going to be a precipitate being formed, meaning it's insoluble. All right, so what does that look like? So the general form of single replacement reactions first, double replacement. Double replacement, also called metathesis reactions. So look at double replacement reactions. Here's my favorite one. Potassium iodide, aqueous solution. I'm going to add to a solution of lead nitrate, also an aqueous solution. Both of these are salts in aqueous solution, so in my own mind, I say, oh, and I got ions in my two solutions as long as they're soluble. I have a binary ionic salt and a ternary ionic salt, each in their own aqueous solution. So I have one container with the potassium iodide, another container with my lead nitrate. So here's the things I put into the aqueous solutions to dissolve. The container with the potassium iodide in it, when I make an aqueous solution, as long as that potassium iodide is soluble, what kind of ions am I going to get into my solution here? Potassium ions, and what's the charge on potassium ion? +1, what else would I have? Iodide ions, which have a -1 charge. Right? In my container of lead nitrate, what kind of ions would I have? Lead ions with what charge? +2, and then I have nitrate ions, but how many of those would I have? My ratios? 2 to 1, right? It's important that you depict them 2 to 1. Alright, now in single replacement reactions, the general form of single replacement reactions, we have AB aqueous solution plus CD aqueous solution. Basically, you just switch the partners, right? Since this is always the positive, negative, you've got to switch the partners, positive, negative, negative. So then you get AD being formed and or CB being formed. And I put them this way because you always put the positive thing first and the negative ion second. So that's the general form of double replacement. Double replacement, usually you'll get one aqueous solution being made. It doesn't always have to be first, but you usually get at least one. And the other one, you will get a precipitate. Meaning it's a solid that comes out of the solution, or a gas. Right? So you get one or the other. You have one that remains in aqueous solution, and the other one is going to be either a precipitate or a gas. That's the general form of double replacement reactions. Alright, so if you look back at the specific one, macroscopically what I would see is I would take the solution of potassium iodide, it would look just like water. It would be clear, it would be colorless, you could see through it, it would be transparent, it wouldn't look any different than water. Same thing with this stuff. It had a solution of lead nitrate, I'd look at it, it would be clear, colorless, it wouldn't have any color to it, I could see right through it, it would look just like water. When I add the two solutions together, what I would see would be bright yellow. Well, holy smokes. I know for sure there was a chemical reaction there because it went from being clear to being bright yellow. Eventually, if you let it settle out over time, the precipitate would settle to the bottom, and the precipitate would be the bright yellow thing. The precipitate is the bright yellow thing, and it would be clear and colorless above the bright yellow precipitate. Alright, what do you suppose the products are of this reaction? Keeping in mind that this is the general form. What's the products going to be? Potassium nitrate, so K and NO3 might potentially have done something. What else could possibly have happened? And some lead iodide, some PB, and some I. Alright, here's where we have to start. We should also do this in single replacement reactions, but it's a little easier in single replacement. In double replacement reactions, you have to start writing the correct nomenclature for the products that you predict. And the nomenclature is based on the charges of the ions as they are here. In redox reactions, the ionic charges change, so that's a little bit more difficult. In double replacement and metathesis reactions, the ionic charges don't change. So whatever the ionic charges were as reactants, they have the same ionic charges as products. So let's go ahead and put those in. So that's a +1, that's a -1, that's a +2, that's a -1. What's the formula for potassium nitrate? Since potassium is +1 and nitrate is -1, what should I do with that formula? I'm good. I'm just going to leave it as is, right? So I'm okay with the nomenclature. Lead, on the other hand, lead has a +2. Iodine's -1. What's the correct nomenclature for lead iodide? PbI2. You must predict new nomenclature for products in order to write this reaction correctly. Just because potassium and iodine combine in a 1-to-1 ratio here does not mean lead and iodine can combine in that ratio. Just because lead and nitrate combine 1-to-2 here doesn't mean that potassium and nitrate are going to combine 1-to-2. You have to write brand new nomenclature for products based on the individual charges of the ions that are coming together. Somebody in the back there had a question. Did I answer it? Behind the I put it here. Is that what you're saying?
Yeah.
Because I had to write new nomenclature for the products. And the products nomenclature is based on the charge of the ions as they come together. Lead's ionic charge is +2, we found out right here, right? It retains that charge in this kind of reaction as a +2. Iodine over here we decided was -1. It still is -1 in this charge. So in order for us to have correct nomenclature for the products, our ionic compound net charge has to be 0, right? So the correct formula for lead iodine is PbI2, not just PbI. Right? Now, is this balanced, this equation? No, I need to balance it. So what can I do to balance this equation? I think I probably need a 2 there, right? Because I need 2 nitrates. And what else could I put a 2 to fix things? I think I put a 2 right there, wouldn't I? Alright, now that equation is balanced, it follows the law of conservation. That's a metathesis reaction. Double replacement. Generally, one of the products is going to be a solid, one of them is going to be an aqueous solution. We'll learn how to use solubility rules when we get to this kind of reaction in lab. From now, what you need to know is you need to be able to recognize what a double replacement reaction is. When I give that to you for the exam, I say, what kind of reaction is this? You say, that's double replacement. For this exam, you will not have to predict the products, but for exam 2, you will. Alright? Okay, let's move on. That's double replacement. All right. There's good animations there. Once again, I expect you to look at those things, make sure that you know what's going on. And we get to combustion reaction. Combustion reactions usually are where you take some fuel and you burn it in air to make carbon dioxide and water. Combustion reactions. Right. Both of these examples, the first one is methane gas. Where you put it in the gas, you burn it in the presence of oxygen. And the methane gas creates carbon dioxide and water vapor. So you can see why it's a fairly clean burning gas. It doesn't make any particulates. The only problem is methane is a greenhouse gas. Carbon dioxide is also a greenhouse gas. So you're still going from one greenhouse gas to another. This particular one is methane. This is propane. This is what you would have like in this little picture here. This is a propane torch. Propane is usually used in your barbecue grills in your backyard. This is the combustion of propane. You need 5 oxygens and you get carbon dioxide and water in combustion reactions as well. All right? Okay, so formula weights. Now we're getting into calculations and we're starting to accrue the skills we need to be successful in stoichiometry. But before we can go on to the skills in stoichiometry, we have to have some interim skills that we use to get us to that point. There's certain things that we need to make sure that we know how to do. The first one is formula weight. Formula weight is also sometimes called molar mass. So formula weight, molar mass, and it has to do with how much does a mole of that stuff weigh. All right, so let's go to the dot cam here. For example, remember 1 mole of anything is how many pieces? Avogadro's number, right? When you look at the molar mass of anything, you use the periodic table, and it turns out to be super handy because the periodic table, bless you. Periodic table, I had some up here, but here's one. Okay. Molar masses on the periodic table appear, right? So chromiums, the molar mass of chromium. There's chromium, molar mass is 51.996. That means if I have 1 mole, I have 6.02 times 10 to the 23rd chromium atoms, they will weigh exactly 51.996 grams. If I have exactly 1 mole of oxygen atoms, they're going to weigh 15.999 grams. So I can't count out that many pieces, can I? I go 1, 2, 3, 4. Now, if you started counting from the moment you were born, and you counted every second of every day, you never took time to sleep, and you lived to be 100, you would never even get close to 1 mole. Right? So that's a lot of pieces. Could I count out a mole of atoms? Probably not, unless I have a lifetime to do it. Can I measure out the mass of 1 mole of atoms? Absolutely. Can I measure out 15.999 grams of something? You bet I can. If I do that, I know that that's exactly 1 mole of atoms. So we can use the periodic table to figure out how to go from what we can't see and we can't measure to what we can see and we can measure. For example, lead nitrate. Again, we use the same thing, turn it around a compound. If I want to know the molar mass, also sometimes called, what's the one that was on the PowerPoint, the term? Formula weight, thank you. Molar mass is generally related to molecular compounds. Formula weight is generally related to ionic compounds. It means the same thing. It means how much does a mole of that stuff weigh? So you look and you say, all right, I want to determine the molar mass or the formula weight of lead nitrate. I say, well, I got 1 lead in a particle of lead nitrate. So 1 ppb times, if you look on the periodic table, the molar mass for lead, what does it say over there? I don't have my good glasses on. 207.2? All right, 207.2 grams per mole. That's the units that I'm using when I'm doing this calculation from the periodic table. I'm using grams per mole. All right, so I've got how many nitrogens are in 1 piece of lead nitrate? There's 2 of them, so I have 2 nitrogens. Each one is 14 grams per mole. Gives me 28 grams per mole. This one is 207.2 grams per mole. Let's put that and that. I've got the nitrogen and the lead accounted for. Finally, I want to account for the oxygen. 6 of them. 6 of those oxygens times, I'm going to round it to 16, right? So 6 times 16 is, thank you, 72 grams per mole. Now if I want to figure out the molar mass of the whole darn thing, I just add these numbers up, right? That's 28.0, so it would be 0.27, 14, is that right? Did I do the math right? 347.2 grams per mole. Those of you with calculators, verify. We have addition right. Alright. 307? Thank you. 307.2. Alright, so that's what we call the molar mass, or the formula weight. We would have to use formula weight for this one because it's an ionic compound, and that's how we calculate it, right? Yes?
What should we put your answer as like a significant figures? Like,
oh, good point about sig figs. On this one, since each of these has different varying levels of precision, just round to tenths. I tend to take whatever you see on the periodic table, round to tenths, and throw it here. Okay, that's usually a good question. Good question. All right, so that's molar mass. All right, there's examples for you. Formula weight, molar mass. Molecular weight, same thing, same process. Percent composition is simply what's the percent of that thing in a particular compound. All right, let's try that with our example that we used before. Let's do percent composition of our lead nitrate. So say, for example, I want to know what's the percent nitrogen in lead nitrate. Right? That was my question. So percent is always the part over total. And since it's a percent, what do I do with the ratio? Times 100. All right. In this case, if I want to know the percent that's nitrogen, what's the part that's nitrogen? Well, we know we got, yeah, right there we go, 28. Thank you. What's the total? 307.2 times 100. That will give me the percent that is nitrogen. Make sense? All right. All right. Finally, we got to talk about moles. Moles is 6.02 times 10 to the 23rd of any of those pieces. That holds true for anything. You can have a mole of bunny rabbits, right? If I had a mole of baby marshmallows, 6.02 times 10 to the 23rd, baby marshmallows, and I put all those baby marshmallows on the surface of the planet. I covered all the continents and all the oceans with baby marshmallows. We would be 6 feet deep in baby marshmallows. So moles will hold up, right? If I had a mole of pennies, I would have to take as my sample for my entire teaching career a single mole of pennies. If I had a mole of pennies, I could spend $1 million a day for the rest of my life. I would have the inheritance left over for my 2 sons, say I lived until like 90, right? I lived till 90, I would have inheritance to give both my sons. They could each then spend $1 million a day for the rest of their lives. If they lived till 90, they would still have money for my grandchildren. So a mole is a lot of stuff. 6.02 times 10 to the 23rd is a lot of pieces. Why do we use a mole to describe a quantity in chemistry like bakers use a dozen? People that do office supplies talk about gross, which is 144. Why do we use a mole in chemistry? Atoms are itty bitty, right? So we got to use a big honking number to describe how many atoms we have. So a mole of anything is 6.02 times 10 to the 23rd pieces of that stuff. So think of a mole as a quantity, like a dozen. All right? It's a rather nebulous term, but I want you to think of a mole as a dozen of those pieces. Right? So molar mass is how much a mole of those things would weigh. Same thing with formula weight. Just add units. There's the number of particles. You can think about atoms versus particles. A good one to look at is here. If I got a mole of nitrogen, it's 6.02 times 10 to the 23rd atoms of nitrogen. If I have a mole of nitrogen molecules, I have 1 mole of molecules, but I have 2 moles of atoms, right? Because each molecule has a mole, or 2 moles in it, 2 atoms in it. So if I have a mole of molecules, I have 2 moles of atoms. All right, we're done for today. We'll pick this up on Monday. And we'll start probably the packet full force on Monday.